Despite living on a tiny planet in a vast cosmic corner, astronomers know precisely how much visible matter the universe should hold. Yet for decades, 40% of it has vanished. And no, I'm not just talking dark matter or dark energy. Galaxy clusters lack the visible mass our models demand. Galaxies have shed massive birth reservoirs. Even intergalactic voids, those cosmic deserts, are emptier than theory predicts. This missing mass is out there, somewhere. Before we hunt down the universe's lost matter, we need to understand what we're actually looking for. This is Michael Alex, and you're watching Vortex. The universe contains three types of substance: dark energy, dark matter, and ordinary matter, what physicists call baryonic matter. Dark energy drives cosmic expansion. Dark matter provides the gravitational scaffolding for galaxies. But ordinary matter? That's everything you can see, touch, or detect with telescopes. Stars, planets, gas clouds, dust. Cosmologists have calculated exactly how much ordinary matter the Big Bang should have produced. The ratio is written into the cosmic microwave background radiation, the universe's baby picture from 380,000 years after the Big Bang. Those temperature fluctuations aren't random. They're a precise recipe encoded in light that's traveled for 13.8 billion years. The math is ironclad. Ordinary matter should constitute approximately 5% of the universe's total mass energy content. That sounds small, but in absolute terms, we're talking about an incomprehensible amount of material spread across billions of light-years. Here's the problem: when astronomers actually count the visible matter in the present-day universe, stars in galaxies, gas between stars, plasma between galaxies, they come up short. Dramatically short. Approximately 40% of the baryonic matter that should exist simply isn't where we expect to find it. This isn't a small discrepancy. This isn't measurement uncertainty. 40% of ordinary matter has gone missing, and the deficit appears across multiple independent observation methods. Galaxy surveys come up short. X-ray observations of galaxy clusters reveal insufficient hot gas. Even direct star counts in the Milky Way suggest our own galaxy is undermass compared to gravitational models. Dr. Xavier Prochaska had spent 15 years building the most comprehensive baryon census ever attempted. His team at the UC Santa Cruz combined data from Hubble, Chandra, the Sloan Digital Sky Survey, and dozens of ground-based observatories. They counted everything: luminous stars, dim brown dwarfs, cold molecular clouds, hot ionized plasma, dust grains absorbing starlight. The numbers refused to add up. "We checked everything 3 times, Prochaska told his research group during a tense meeting in 2018. Instrument calibration, statistical methods, systematic errors. The deficit persists across every independent dataset. Galaxy clusters presented the most glaring evidence. These massive structures, the largest gravitationally bound objects in the universe, should contain enormous reservoirs of hot gas. The gas exists. X-ray telescopes detect it clearly, glowing at millions of degrees between the galaxies. But when researchers calculate the total mass based on temperature and X-ray luminosity, the numbers fall short of what galaxy formation models predict. The missing mass problem extended beyond clusters. Individual galaxies showed the same pattern. Astronomers could measure a galaxy's rotation speed, which reveals its total mass through gravitational physics. They could count its stars and estimate stellar mass. They could detect its hydrogen gas through radio observations. Yet when they added everything together, the sum equaled only 60% of what gravity demanded. Something was missing. Something massive. The intergalactic medium, the vast space between galaxies, presented an even stranger mystery. Cosmological simulations showed that galaxies form from massive gas reservoirs that collapse under gravity. As stars ignite, they heat and blow away leftover gas. This expelled material should still exist somewhere in intergalactic space. It can't simply vanish. But observational searches came up empty. The cosmic voids, those immense stretches of near-nothingness between galaxy filaments, were even emptier than theory predicted. If the missing gas wasn't in galaxies, and it wasn't in voids, where had it gone? Prochaska's team considered every possibility. Perhaps the missing matter had collapsed into black holes too small to detect. Perhaps it existed as free-floating planets ejected from solar systems. Perhaps it had formed extremely faint dwarf galaxies below current detection limits. Each hypothesis failed under scrutiny. Black holes that massive would produce detectable gravitational effects. Free-floating planets couldn't account for 40% of all baryonic matter. The numbers were astronomically wrong. Faint dwarf galaxies might hide some mass, but not nearly enough to close the gap. The scientific community split into camps. Some researchers argued the problem lay in our galaxy formation models. Perhaps galaxies were more efficient at converting gas into stars than simulations predicted. Others suggested our understanding of cosmic chemical evolution was incomplete. A few proposed exotic physics. Perhaps baryonic matter could transform into something undetectable under extreme conditions. But Prochaska suspected something simpler and more humbling. The missing matter wasn't missing at all. It was hiding in a phase or location that telescopes simply couldn't see. Think about what that means. Humanity has built instruments capable of detecting individual photons that traveled for billions of years across space. We can measure the chemical composition of stars thousands of light years away. We can image black hole event horizons. We've detected gravitational waves from colliding neutron stars. And yet 40% of ordinary matter, not exotic dark matter, but regular hydrogen and helium, had managed to evade every detection method we possessed. The missing matter existed somewhere between absolute vacuum and detectable density. Too diffuse to glow like a star. Too hot or too cold to emit radio waves efficiently. Spread across such vast distances that it blended into background noise. It was out there. The cosmic microwave background guaranteed it. The Big Bang had produced that matter, and matter doesn't simply cease to exist. Conservation of mass energy is one of physics' most fundamental principles. The question wasn't whether the missing matter existed. The question was, where could 40% of the universe's ordinary matter hide for billions of years without being detected? Prochaska stared at the baryon budget spreadsheet on his screen. 40% missing. 40% unaccounted for across dozens of independent measurements. 40% of matter that should be screaming its presence across every wavelength remained silent. The universe was concealing something in plain sight. And if humanity's most sophisticated instruments couldn't find it, the hiding place had to be somewhere no one had thought to look carefully enough. Somewhere between the galaxies. In the vast cosmic web of filaments connecting galaxy clusters. In a state of matter so diffuse and so precisely the wrong temperature that it had slipped through every observational net. The missing matter was out there in the darkness between the stars. And the hunt was about to end. The discovery, the proof, and the revelation. The answer had been hiding in the space between spaces, in the cosmic web itself. For most of human history, astronomers assumed the universe was relatively uniform. Galaxies scattered randomly across space like grains of sand on a beach. But as telescope surveys mapped larger volumes of the cosmos, a stunning pattern emerged. Galaxies weren't randomly distributed. They clustered along filaments, vast threads of matter stretching across hundreds of millions of light-years. Between these filaments lay enormous voids, cosmic deserts where almost nothing existed. The universe resembled a three-dimensional spider's web, with galaxies as bright nodes where filaments intersected. This structure, the cosmic web, wasn't just beautiful. It was the key to everything. The filaments connecting galaxy clusters weren't empty space. Simulations predicted they should contain diffuse gas heated to temperatures between 100,000 and 10 million Kelvin. At these temperatures, hydrogen wouldn't be cold enough to form molecules or hot enough to emit strong X-rays. It would exist in a phase astronomers called the warm-hot intergalactic medium, WHIM for short. Theoretically perfect for hiding matter. Too hot for radio telescopes. Too diffuse for X-ray detection. Spread across such immense distances that its presence would be nearly invisible against the background glow of the universe. If the missing baryons existed anywhere, they existed here. But theory and observation are different challenges entirely. Proving the WHIM existed required detecting something almost designed to be invisible. In 2012, a team led by Fabrizio Nicastro made the first tentative detection using the XMM-Newton space telescope, observing distant quasars whose light passed through intervening gas. That gas left dark absorption lines in the quasar spectrum, signatures consistent with highly ionized oxygen at temperatures between 1 and 10 million degrees. Exactly the range predicted for the WHIM. Tantalizing, but not definitive. Prochaska knew what was needed: systematic observations of multiple sightlines through confirmed filament locations. In 2014, Sebastiano Cantalupo provided the roadmap by directly imaging portions of the cosmic web for the first time, enormous filaments of glowing hydrogen extending far beyond distant quasars. Now astronomers knew exactly where to point their instruments. Prochaska's team began analyzing archival data from multiple X-ray observatories, focusing on cosmic web filaments where quasar light would pass through the intervening gas. The work was painstaking: hours of exposure time per quasar, faint absorption lines barely distinguishable from noise. But slowly, patterns emerged. Quasar light passing through filament locations consistently showed absorption signatures: ionized oxygen, ionized neon, temperatures falling in the warm-hot range. The absorbing gas was substantial. Far more than isolated clouds could explain. In 2017, the XMM-Newton telescope confirmed a bridge of hot gas linking two galaxy clusters separated by 10 million light-years. That single filament contained nearly as much matter as the clusters themselves. The pieces were falling into place. The gap between theoretical predictions and observations, that missing 40%, matched almost perfectly with the warm-hot intergalactic medium mass. But science demands reproducibility. In 2019, Hideki Tanimura's team at the Institute of Space Astrophysics turned to archive data from the Planck satellite, exploiting a phenomenon called the Sunyaev-Zel'dovich effect, the subtle distortion created when cosmic microwave background photons scatter off hot electrons. Instead of observing individual filaments, they stacked observations of 260,000 galaxy cluster pairs simultaneously. Random noise averaged out. The genuine filament signal accumulated. The stacked data revealed a clear, statistically significant detection of gas at 1 to 10 million Kelvin threading through the cosmic web, harboring approximately 30% of all baryonic matter in the universe. Combined with matter in galaxies, hot cluster gas, and cold clouds, the census was finally complete. But Prochaska wanted more than statistics. He wanted to see a specific filament, to point at a region of space and say with certainty, there it is. That moment came when an international collaboration focused on the Able 222 and Able 223 galaxy clusters, combining X-ray observations, optical surveys, and gravitational lensing. Between the two clusters, at roughly 10 million light-years apart, a bridge of hot gas-emitting faint X-rays glowed with billions upon billions of solar masses of hydrogen and helium, heated to 10 million Kelvin, stretched across millions of light-years. Prochaska examined the X-ray images late one evening in his office. The filament appeared as a faint, elongated glow connecting two bright nodes. Subtle. Easily missed. But undeniably real. He thought about the decades-long hunt. The confusion when galaxy censuses came up short. The hypotheses that failed one by one. And now a direct image, proof that the universe's missing matter existed exactly where the mathematics predicted. The discovery, however, was only the beginning of understanding. The cosmic web wasn't merely a storage depot. It was an active, dynamic structure governing how matter flowed throughout the universe. As dark matter clustered in the early universe, it created invisible scaffolding. Ordinary matter followed, falling into filaments and accelerating under gravity. When those gas streams collided at hundreds of kilometers per second, kinetic energy converted into heat through accretion shock heating, not from stars or black holes, but from gravity itself. This explained the extreme temperatures, millions of degrees sustained by the violence of cosmic structure formation. Yet the gas remained stable. Hot enough that thermal pressure resisted further collapse into galaxies. Not diffuse enough to drift into voids. Trapped in a Goldilocks equilibrium threading through the cosmic web for billions of years. Galaxies pulled matter from nearby filaments. Supernova explosions and black hole jets pushed enriched material back out. The cosmic web functioned as a vast circulatory system, matter cycling between galaxies and filaments across cosmic time. Prochaska's collaborator, Dr. Marcus Chen at MIT, ran simulations revealing deeper complexity. Individual filaments contained gas at 100,000 degrees, 1,000,000 degrees, and 10 million degrees simultaneously, different phases coexisting within the same structure. The filament connecting the Coma cluster to Able 1367 showed a dense, hot spine reaching 8 to 10 million Kelvin at its core, cooling to 1 to 2 million Kelvin at its edges, transitioning to phases below 100,000 Kelvin at its boundaries. Not a simple tube, but a complex, stratified atmospheric system controlling how galaxies fed and evolved. The cosmic web wasn't background structure. It was fate itself, determining how galaxies acquired matter, how fast they formed stars, and how they would eventually die. Prochaska stood before a packed auditorium at the American Astronomical Society winter meeting, the culmination of 2 decades of work projected behind him, the cosmic web in 3 dimensions, filaments rendered in shades of red and orange representing temperature. For years, we asked the wrong question, he began. We asked, where are the missing baryons? As if matter had somehow gotten lost, misplaced in cosmic accounting. But matter doesn't get lost. It simply exists in states we hadn't learned to detect. The warm-hot intergalactic medium was more than found matter. It was a paleontological record, each temperature regime encoding when and how gas fell into the cosmic web over billions of years. It was also the universe's remaining fuel supply. Cold molecular clouds had mostly been consumed. Hot cluster gas was too tightly bound to reach most galaxies. But filament gas, at intermediate temperatures, remained accessible. Current models suggested it could sustain star formation for another 5 to 10 billion years before the universe entered its long, slow decline. The cosmic web determined not just where galaxies formed, but when they would die. Later that evening, Prochaska sat in his hotel room and pulled up the baryon sensors one final time, the spreadsheet that had consumed years of his life. Every column was filled. Every percentage accounted for. Galaxies, clusters, cold clouds, and the warm-hot intergalactic medium threading through cosmic web filaments. The numbers matched theoretical predictions with stunning precision. 40% of ordinary matter had been hiding in the space between galaxies, heated to millions of degrees, spread across structures so vast and diffuse that early instruments simply couldn't see them. The universe concealed nothing. It simply required us to ask the right questions, look in the right places, and wait for instruments sensitive enough to detect the answers. Prochaska closed his laptop and looked out at the night sky. Somewhere up there, invisible to human eyes, the cosmic web stretched across unfathomable distances. Filaments of superheated gas connecting galaxy clusters. Rivers of matter flowing between structures. The hidden circulatory system of the cosmos finally revealed. The missing matter had been found. The cosmos had shared its secret. And the universe was far more beautiful, far more complex, and far more interconnected than anyone had imagined. If you found this cosmic detective story fascinating, hit that like button and subscribe to Vortex for more discoveries that reshape our understanding of the universe. And drop a comment below, where in the world are you watching from? Let's build a global community of cosmic explorers. The hunt for missing matter is over. But the journey through the cosmos continues. Stay curious.